Hello everyone. In this video, we're going to look at techniques for evaluating integrals that involve powers of sines and cosines. So we're going to look at techniques for evaluating indefinite integrals that look like this. So we have the indefinite integral of sine to some power times cosine to another power. Now it's fair to ask, why do we care about evaluating antiderivatives for functions of this form? Well, as we'll see later on, when we study the integration technique called trigonometric substitution, when we apply trigonometric substitution, we're going to encounter integrals that look like this that we will have to evaluate. And trigonometric substitution is a very important integration technique because it allows us to evaluate integrals that involve things like the square root of 4 minus x squared or the square root of 1 plus x squared. So integrals that involve functions that look like this, we can use trigonometric substitution with. And when we use trigonometric substitution, we will oftentimes encounter integrals that look like this in an intermediate step that we have to evaluate. Okay, so before we look at the techniques for evaluating integrals like this, let's note something. Now, first of all, let's recall what it means for an integer to be even or odd, its precise definition. So when an integer m is said to be even, like 2, 4, 6, 8, and so on, that means you can write it in this form. So an even integer can be written as 2 times some other integer. For example, 4 is 2 times 2. 6 is 2 times 3, of course. 8 is 2 times 4. Right? 10 is 2 times 5. So even integers can always be written in this form. 2 times some other integer. Now, if m is an odd integer, like 1, 3, 5, 7, 9, 11, and so on, then that means that it can be written in this form. 2 times another integer plus 1. For example, 3 is 2 times 1 plus 1. 5 is 2 times 2 plus 1. 7 is 2 times 3 plus 1, and so on. Okay? So keep that in mind when we're doing these problems. Even integers take that form. Odd integers will take this form. Now here we have a table that summarizes how to handle integrals of this form in different cases when the m and n are odd or even integers. So the first case we're going to consider is when the power of sine is odd and positive. So when the m right here is an odd and positive number, so 3, 5, 7, 9, so on. So down here is how we're going to do an integral when we're in that case. So here we have the m rewritten as 2 times k plus 1, right? If m is odd, then we can write it in this form, 2 times k plus 1. And what we're going to do here is move one of these signs over and put it with the dx. So you see that's exactly what we have right here. So you notice we just took one sign away and joined it with the dx. Now we're going to write the sine of 2 to the k power as sine squared raised to the k power. All right, you see that? That's just using properties of exponents, right? That's using the property that x to the a times b equals x to the a raised to the b power, right? That's just using that property. And now we're going to use a trig identity. So we're going to replace sine squared with 1 minus cosine squared, right? That comes from this trig identity right here. Okay, and that's our Pythagorean identity. You might also see that written as just sine squared x plus cosine squared x equals 1, right? So if you move the cosine squared over, you get sine squared equals 1 minus cosine squared. And so there we go. We replace the sine squared with 1 minus cosine squared. And now what we can do is use a substitution u equals cosine x, in which case du is going to be negative sine x dx. And so you see what happens when we use that substitution at this step right here is the sine x dx becomes negative du. This is going to become u squared. Cosine squared is going to become u squared. Cosine to the nth power is going to become u to the nth power. And then what we have is we end up with this integral down here. Now you see what we have here is 1 minus u squared to the kth power times u to the nth power. Now this is just going to be a polynomial in the variable u. And we can easily integrate polynomials. So what we'll do then is we'll integrate this as a polynomial, and then we'll go back and we'll substitute in place for all the u's cosine x, and we'll get our answer. So we'll take a look at an example using case 1 here in a second. Let's go over case 2 and then case 3, and then we'll do some examples. Now here we have case 2. This is going to be the case when the power of cosine is odd and positive. Now that's going to be very similar to the case that we just considered for when the sine had an odd and positive power. It's basically going to be the same, except the sine gets replaced for the cosine. Alright, so you see what we have here is if the power of the cosine is odd, then we can write it as 2k plus 1. And then we can pull away one of these cosines and put it with the dx. So you see right here we have this is cosine to the 2k plus 1 right here, and one of the cosines is paired off with the dx. And now we rewrite cosine to the 2k power as cosine squared to the kth power. And now we replace cosine squared with 1 minus sine squared, right? Using this identity right here. That comes from the identity sine squared plus cosine squared equals 1. And now at this point, we can let u equal the sine of x, in which case du is going to be cosine x dx. So you see this piece is going to become du, and then this is going to become u to the mth power. What's in here is going to be 1 minus u squared, and then raised to the k power. And what we end up with is this integral down here. And once again, this is going to be an integral involving a polynomial in the variable u. You can FOIL it out and it would be a polynomial in u. And then you can integrate it. We know how to integrate polynomials. And then after you integrate it, replace all the u's with sine x, and you'll get your answer to the original problem. Now let's take a look at case 3. Now down here in case 3, we're going to consider what happens when the sine and cosine have even and non-negative powers associated with them. Well, in that case, what you're going to do is to use these two identities. So you're going to replace sine squared in your integrand with 1 minus cosine 2x over 2. That's a trig identity. And any place you have a cosine squared, you're going to replace it with 1 plus cosine 2x over 2. And then you'll FOIL out the integrand, simplify it, and then you go back and you reapply steps 3 and step 2 up here as needed. Now we'll take a look at an example illustrating this case to clarify it. This is probably the more difficult case to execute. Alright, so let's take a look at a few problems down here. So here we have an example where we want to evaluate the antiderivative of sine to the 5th power times cosine to the 4th. So we see that here we are in case 1 because the sine has an odd power right there. So what we're going to do is take one of these sines and put it with the dx. And then we're going to use the substitution u equals cosine and du equals negative sine dx. So let's do this. So down here we have our integral. Move one of the sines away and put it with the dx. Okay, so there we have it. This then becomes sine to the 4th power, and we write sine to the 4th as sine squared squared. Okay, now this term right here, the sine squared, we replace that with 1 minus cosine squared. You see, that's why we write it like this. Okay, we write it, we had a sine to the 4th left here. When we move the one sine over to the dx, and you have to write this as sine squared to some power, well, and that power is going to be 2 in this case because 2 times 2 is 4. Okay, and now you see at this point right here, you see you can let u equal cosine as we stated right here, and then the du part is going to become this, or actually negative du. This is going to become negative du. And so using the substitutions up here at this step right here now, all the cosines are going to become u's, so we get 1 minus u squared squared, u to the 4th, and this becomes negative du. So there's the negative out in front there, du. Alright, now this is just a polynomial in the integrand, and we can evaluate it. Now we do have to simplify it a little bit, okay? Keep in mind, okay, we have to FOIL this out, so what we're going to get there is, this is going to be like that, and then we need to multiply by u to the 4th, so this is going to become u to the 8th. This will become u to the 6th, and then this will be u to the 4th. Okay, so that's what we have right down here. Okay, and we just move the negative back inside there. All right, and now this can be integrated. Antiderivative of u to the 8th power, that is u to the 9th over 9, and we have that negative there. Antiderivative of u to the 6th is u to the 7th over 7, and the 2 carries down. Antiderivative of u to the 4th is u to the 5th over 5, and then plus c. And then at this point, you simply replace all the u's with the cosine. And here's your answer. So right there is the antiderivative for this function up here, sine to the 5th times cosine to the 4th. Let's take a look at another example. Now let's note here for this example that sometimes the previous guidelines will even work when the powers of m and n are not integers. So that's what we're going to consider here. So those guidelines can work even if the m and n are not integers. So here we want to evaluate a definite integral, the integral from pi over 6 to pi over 3 of cosine cubed x over the square root of sine. Alright, now we see a cosine cubed. So you see, what you have here is you have cosine cubed x. This is the way you want to think about it. So if I pull one of these cosines away and put it with the dx term, right, then we could let u equal sine, and cosine x dx, if we pull one of these away, that would become a 2. And then if we let u equal sine, this is going to become our du part, and that's what we'd like. Okay, so that's what we're going to do here. We're going to, right here, we pull away one of the cosines, put it with the dx. So you see, that's what we did right there. Now the cosine squared, and then we have a cosine squared left right here. We can write that as 1 minus sine squared. And now we can let u equal sine. We see here, because this is going to become our du. Du is cosine x dx, so you see that becomes our du then. Now let's see how our limits of integration change. Okay, those two are going to change under this substitution. So u of pi over 6, if I put pi over 6 in for x, the sine of pi over 6 is 1/2. So this will become 1/2. Right there we have it. And if we put pi over 3 in for x here, the sine of pi over 3 is root 3 over 2. Okay, so there you go. We changed the limits of integration to 1/2 and root 3 over 2. Now, let's also note that what we get in the integrand here is 1 minus u squared. See that? Divided by the square root of u. There it is, du. Okay, this part becomes du, right? Now what we can do is evaluate this by breaking up this fraction, writing it as 1 over the square root of u minus u squared over the square root of u. And you notice that that is u to the negative 1/2 minus u to the 3/2, right? Okay, 2 minus 1/2 is the 3/2. And then we can integrate this piece right here, okay? So the antiderivative of u to the negative 1/2, all right, remember you have to just add 1. And add 1 here, and then divide by the same number, okay? So when I add 1 here, integrating this, we get u to the 1/2. Negative 1/2 plus 1 is 1/2. But then we need to multiply by 2 so that the 1/2 cancels with the 2 if we were to differentiate. 3/2 plus 1 is 5/2. So u to the 5/2 right there. And we need to multiply by 2/5, so if we were to differentiate, 5/2 and 2/5 would cancel. And then we just evaluate from 1/2 to root 3 over 2. So, you just have to plug root 3 over 2 in for the u's. So here they are. Then plug 1/2 in for the u's. Here they are. And subtract. And you can evaluate this on your calculator, and you'll see that you get approximately 0.239. And that's going to be our answer. Okay, so that's how we handled this problem. This was a problem that was a case 2 type problem. Even though the m and n were not integers, in particular the m was not an integer, we could still handle this problem. Let's take a look at one that is in case 3 now. So now here we want to evaluate the antiderivative of cosine to the 4th power of x dx. So you see the m is 0 in this case, and the n is 4. So they're both even, so we are in case 3. Alright, so what we want to do here is use this substitution. Cosine squared x equals 1 plus cosine 2x over 2. That is a trig identity. Okay, we're just telling you that's the one we use. So you write the cosine to the 4th power. You write that as, put one little intermediate step in here, you write that as cosine squared of x squared. And then for the cosine squared, you put in this right here. Okay, so there we go. We have it in there. Now you just have to FOIL this out. Okay, now you can move that 1/2. There's a 1/2 here, squared. That's 1/4. Move it outside. All right. And then when you FOIL out the rest, 1 plus cosine 2x squared, you just have to FOIL that out. That's going to be okay, so there it is FOILed out. Okay, so we end up with this. Now, if you look at this part right here, no problem. We can integrate this piece right here. We don't have any powers of cosine. We just have a cosine. This would require a little substitution. If you want to find the antiderivative of cosine 2x, you do have to do a little substitution. You don't have to do the substitution. You could realize that, okay, the antiderivative of this is going to be the sine of 2x. But if I were to differentiate this, I would pick up an extra 2 when I apply the chain rule. The derivative of this is going to be cosine 2x times 2. So we have to multiply this by 1/2. Okay, so there's the antiderivative of cosine 2x, ignoring the constant. So this is no problem to integrate. The 1 is no problem. Okay, the antiderivative of that is just going to be x. But now we still have this cosine squared right here. Well, you see, we're going to reapply this identity again for this piece. Okay, so you see what we have here is the cosine squared of 2x reusing this identity. Okay, so this is going to be a 2x instead of an x, and that's going to make this right here a 4x. We end up with this. Cosine squared 2x equals 1 plus cosine 4x over 2. And we put this in place of the cosine squared. All right, so now what we end up with is this. So this whole integral right here becomes this. So we get 1/4 integral 1 plus cosine 4x over 2 dx. Okay, so that's our cosine squared. Plus 1/4 times 2 is 1/2 integral cosine 2x. Plus, and then we have the 1/4 times 1, or just 1/4 times the integral of 1 dx. All right, this one right here, we can just do a little simplifying, move the 2 out. So we get 1/8 integral 1 plus cosine 4x plus, and then the rest of this is just repeated down here. Okay. Now we can integrate all of this. Well, let's simplify a little bit here. What we have is 1/8 times 1 is going to be 1/8. Add that over here to the 1/4, right? The 1/4 times 1. So 1/8 plus 1/4 is 3/8, right? So that's where this 3/8 comes from, times 1 dx. Okay. Just a little simplifying there, so we got rid of this 1. So then what we have is the 1/8 times the integral of cosine 4x. That's this right here. Cosine 2x, that's right here. And then the 3/8 times the integral of 1 dx. And now everything can easily be evaluated. Antiderivative of cosine 4x, let me just put that over here. So that's going to be the sine of 4x. But you have to keep in mind, if I were to differentiate this, I would pick up an extra 4, so we need to divide by 4. Okay? And when we multiply by 1/8, we get 1/8 times 1/4 gives us 1 over 32 sine 4x. So this is this piece right here. Okay? This piece right here. Okay? Antiderivative of cosine 2x is 1/2 sine 2x, and then times 1/2. So it's going to give you a 1/4 sine 2x. And then 3/8 times the antiderivative of 1 dx, is really a 1 right in there, is just going to be 3/8 times x. And so here is our answer. And that is it. So you see what we did here. We had to apply case 3 2 times as we did this problem, right? So we had cosine to the 4th. We had to write it like this. Apply the trig identity. Foil it out. Then we still had a cosine square term, so we had to reapply this identity again until we knocked everything down until we only had cosines to the 1st power, right? That's the way this problem worked out. And so that concludes this video about integrating powers of sines and cosines.